Welcome to the Automotive Diagnostic Podcast. We're going to explore ways to sharpen our diagnostic skills, find learning resources, and hear from experts in the automotive field.
Hey, what's going on, automotive world? Welcome to another episode of the Automotive Diagnostic Podcast. My name is Sean Tipping, and I am just getting over a cold, so I apologize about my voice. It sounds like I've been smoking a pack of cigarettes for a number of days now. Joining me on the show this week is Mitch Minton. Mitch has been on the podcast before to talk about CAN bus decoding, really interesting stuff. I will link that episode in the show notes as well, but he is an extremely smart individual, and particularly when it comes to networks on vehicles and CAN bus, he's going to help me out with a few other network areas of the vehicle. This is a listener question that I got when I did the listener Q&A a while back. I got a whole bunch of questions that we didn't get to. One of them was asking about the SENT protocol, which is communication between a sensor assembly and a control module, Ethernet used in automotive applications, and DoIP. So Mitch is going to help me tackle those topics along with talking about CAN bus in pretty good detail, vehicle security, just connection to your vehicle in general, what that means. Really, really cool stuff. So I enjoyed this talk quite a bit and learned a bunch. Hopefully you will as well. With that out of the way, let's jump in. All right. Good afternoon, Mitch. How you doing?
I'm doing well. How about yourself?
I'm good. I am good. I'm, like I mentioned before, I'm just getting over a cold. So for everybody listening, I'm sure my voice is a little different than normal, but this is the best I have sounded in 5 days. So I'm happy about it, but I had no voice this week at all.
I'll try to carry the weight here.
That's fine with me. I was telling everybody, I mean, even now I sound like I've been smoking for 30 years or something like that. So.
Yeah. It happens to the best of us, usually in wintertime. It's just the way it goes, I guess, you know?
Yeah. It's, it could be a lot worse. So,
right.
Yeah. What's new with you? What's going on in the racing world?
So today, since it is Sunday the 29th, the Rolex 24-hour race just ended. I'm not working it, obviously, but I do have some colleagues that I've done work with. Colin Braun, he took the Daytona prototype first place.
Nice.
And then there's a few other people that I am familiar with around the paddock that I've maintained communications with when I'm in the racing world. LMP2's Thomas Merrill took first place as well. Everybody else did okay, I guess. Some didn't do so great, but 24-hour race is the most enduring race that you'll probably ever see any cars get put through. So,
okay.
A lot of people don't look at it this way when you're in the racing world, but just finishing that race is an impressive feat in itself. Getting a car to last 24 hours of nonstop, just brutal endurance. It says something, and it takes a lot of time, talent, and resources to make it happen.
Yeah, I mean, how many cars start and how many finish in a 24-hour race?
So 61 cars started in the field this year. I think 61's their cap.
Okay. Of
the 61, I don't know how many finished, but usually about one third of the field won't make it.
Wow.
Won't make it to the end. So you usually end up with in the low 40s range for cars that can complete. Some of them, you have to start and end with the same powertrain too. So you can't just hey, our engine blew. We're going to pull it into the pits. We're going to change the engine, throw it back out there. That's one of the stipulations that can't happen. So you have to start and finish with the same powertrain. So if your gearbox destroys itself, you're out. If your rear end destroys itself, you have to start and stop with the same housing. So if your housing is broken, you're done. If your engine's broken, you're pretty much done. So it's not even there's a lot of luck associated with it, in my opinion. You can do everything, you can prepare for everything, and you may not make it to the end, and that's just the name of the game.
Dang, that's crazy. And it's the same driver the whole 24 hours too?
Oh, no. They have four drivers. They have stipulations based on classes, but I think the longest you can run is 4 hours in one stint.
Okay. I was like, that's pretty nuts if it's the same guy.
Yeah, no. That would be so bad. So bad. Half of them wouldn't make it to the finish line that way. No, it's, they'll go about 4 hours, usually, max. And then I think there's a minimum rating per class, and then there's a maximum rating per class. And in fact, there's one team I know that actually went to the GT. They call it GTD Pro, and they have two classes. One's GTD and one's GTD Pro. The GTD Pro class is considered you can have all pro drivers or all like rated professional drivers. While the GTD class, you have to have, I think it's one, it may be two silver and bronze drivers. So you end up with this, and you have to have a minimum time with those silver and bronze drivers in the car. While in the GTD Pro, they just have like a general rule. And a team that I'm communication with some of the people that work with the team, and one of the drivers, they actually went in on GTD Pro so they could keep the silver drivers down on time frame because they wanted just the pro drivers to run more.
Okay.
It was a bold strategy to deploy, and it also the amateur drivers that are running on the team. One of them's pretty old, up in the ages, so I can understand why he would potentially want to go. Well, let's go GTD Pro because I'm not interested in sitting, 6 hours or 5 hours in the car. I only want to do like a 2.5, or an hour here, an hour there, and I'm funding it, so this is what we're doing, right?
Okay, sure.
A lot of rules, a lot of regs, a lot of classifications, just tons of grunt work.
Okay. And you're still doing like the data analysis side of things for them, right?
So to some degree, I do a little bit of data analysis. Most of the stuff I'm doing now, I ended up taking a full-time job with a local firm doing ADAS recalibrations and programming and some other mechanical work, basically things that collision repair shops want to sub out.
Okay.
And so since I took that job's Monday through Friday, I did bring up the opportunity because I did have a position that I could have taken, encountered with the Aston Martin racing team for IMSA, but it wouldn't be enough work for me to survive on. So it's like, hey, am I able to do this too? And they were basically said, we'll approach it when it gets closer. But that's not what we're interested in. We're interested in a Monday through Friday full-time employee. But we'll see. So the answer shorthanded was no,
Okay.
There is things that I still do for various race teams on the back end, for basically either reverse engineering signals or getting their data acquisition systems where they should be. And where, if they're like, hey, we're missing something, or we want to make sure things are set up appropriately. And if anything that revolves around CAN, my name's out in the field a little bit. So people do reach out to me and say, hey, I'm looking do you have anything on this card? I'm like, nope, but you have XYZ acquisition equipment. Yep. Do this, that, send me a log. We'll get some stuff squared away for you. It's just the name of the game, I guess. Once people know what you're capable of, and it's kind of a very minor, there's not a lot of people out there doing a lot of CAN bus reverse engineering, right? Or efficiently doing it.
Yeah.
You become a little bit of you stand out in the crowd a little bit. So, I still do a little bit here and there, doing some other stuff with an electric vehicle, an F-150. They wanted to be converted to an EV driveline.
Okay.
They want the dash to work like it should, which I understand. It's a heavy end process, but we're getting there. And so, just little here, a little there. Nothing taking over full time realms of my timeline. I'm typically doing it on nights and weekends.
Sure. How's the ADAS stuff going? Are you doing a lot of calibrations, programming, a little of both, or what?
A little bit of both. I'm learning as I go. Kind of threw my feet in the fire pretty aggressively. One of the big things to understand that it comes with the experiences is when you don't have the information you're looking for, how to efficiently find it, right?
Mm-hmm.
If I've got all these resources that were basically given to me to find out what I need in order to solve the problem or get the job done. The problem I'm having with it is being a novice to navigating various sites like the OE data for navigating various OE applications, all data, Identifix, all these like applications, is figuring out what keywords you're searching for, right?
Sure. Yeah.
So if you type in front radar, you may not get what you need, but like typing in millimeter somehow gets you there. You're right. So it's things like that you got to catch on to and go, okay, this is what they're looking for, even though that's the catchphrase. You got to know the catchphrases and know the keywords you're looking for in order to efficiently search and navigate. And so that's the barrier to entry for anybody, in my opinion, because it doesn't come overnight. They expect me, they're like 6 months to a year. We expect you to be running smooth, which I personally believe it'll probably be 3 to 6 months. I do pick up things relatively quickly, and can kind of understand, and knowing how to think like an engineer and think like a developer and think like a programmer typically helps me.
Okay.
So I do that. I do that a lot. Is like, if I was going to build this, where would I put the information, or why would I put the information here or there? Or so I do try to step out of my own box and go, well, this is what I'd call it. Be like, no, I got to think like somebody else. What would somebody else call this?
Yeah, sometimes I run up against that too, and they did engineer something some way. I was working on a Volvo the other day, and I couldn't understand it all. I'm like, why is this relay underneath this other set of relays that you have to remove and disconnect everything to test it, but then there's no power going to it to test it? I'm like, that makes no sense in my head. Yeah. So yeah, but I'm not an engineer, so maybe that's why.
No, and the things that knowing what I know on the back end, a lot of this stuff, like for instance, the teams that work on something, they'll tell you, here's your box, right? And this is what you need to do inside that box, right? And then halfway through, things get brought up like, well, we still need more things inside this box. And they're like, okay, well, now we have to go take out of somebody else's physical space in order to make it happen. So we got to go we need to go talk to the starter development team or the casting department to try to find a way. Hey, can you change this? Because we don't have physically enough space in order to do what we need to do. Right.
Okay.
And it's those things that you have to play into. There's so many engineers, there's so many like hands in the mix that something's going to get thrown on the back end and they go, well, I just need you to solve it. Like they're like, well, this isn't efficient. And you're like, yeah, I get it. As a manager, I understand. Like, we're not going to make this thing ideal for everyone. This is going to be the Achilles heel of the car. Right. Yeah. And even in the racing world, you see that, and you'll hear about it for like, a good example is you have to end with the same driveline in the 24-hour race. Right. So I think it was Audi actually built their gearbox to actually like basically slide out and slide in, because in the Le Mans race, to my knowledge, you could run a different gearbox. You could swap them out, and they serviced it to where you could do it in about 8 minutes in a pit stop. Wow. So halfway through the race, they'd swap the rear end out, and then you're back to running. And in the Daytona or the IMSA series, regulations, you couldn't do that. So they actually re-engineered the entire rear end of the car in order to make it feasible to actually race it. And if you had a problem, you could pull the gear set out, put a new gear set in, and be on your way.
Okay.
So you end up with, and the racing world's a little bit different because there's like, it's not a cost conscious mindset, right? The goal is to win the race,
performance,
no matter the cost.
Yeah.
But in the OE world, we have defined limits, we have defined timelines, we have defined frames to work within, and we care about cost because we're building 10 million of these, right? And not 20.
Yep.
So you end up with the situation of, if you can save money doing things a specific way, or lightening how much material you use, you're going to do so most likely, because it's just the name of the manufacturing world.
Yeah. If you can save $1 on every car and you make 1 million of them, it's pretty simple. Okay, let's do that.
Right.
So yeah, that makes
CEO's
sense.
got to make that living. CEO's got to make that money.
Exactly. Well, I wanted you to join me on the episode today. I had a bunch of listener questions a while ago. I did a listener Q&A, and I got way more questions than we were able to cover in a period of one episode. So I'm kind of chipping away at them here as I go.
Yeah.
And one of the questions I got, somebody asked me about some vehicle network stuff, specifically the CENT protocol, Ethernet on automotive applications, and the DoIP diagnosis over internet protocol.
Yep.
So I do have some experience with the CENT system on a couple different vehicles. The other two I've only read about. I don't have any firsthand in-field experience, and so I was reaching out to some people to see who wanted to help me out with this topic, and I think you're the perfect person to help me tackle this. So
I don't know. So your experiences are probably about as vast as mine when it comes to essentially all three protocols, right? I focus on one. But it doesn't mean that I don't understand or don't have some knowledge and a little bit of background experience on the others.
Okay.
But we'll chip away and see what we can find out. I'm not a professional on them. I haven't spent the last decade of my life trying to understand it on any of the other protocols for a handful of good reasons.
Sure.
But yeah, let's see what we got. Let's see what we can get solved here.
I like it. Yeah. I mean, my strong suit on vehicle diagnosis is CAN as well. And now I don't understand it in the aspect that you do when it comes to like, hey, let's solve this problem on this car. That's my strongest, I would say, network area is CAN, because I deal with it so often.
Right.
So these other ones, this is new to me, but it also it sparks my curiosity for the future, because you start looking. I was doing some reading. I'm like, okay, well, this is going to be applied, to all of these vehicles going forward, and already is on a lot of them that are out there.
Yeah.
What do we do when we run up against it? So, we can start with the CENT, because I think that's much easier to grasp compared to maybe the other two. And like I say, I actually do have a little bit of firsthand experience with it.
So the CENT protocol is basically stands for with single edge nibble transmission, I believe.
Mm-hmm.
So essentially it is its own, it's asynchronous. It only goes one way. So there's no transmitter and receiver. The only experiences I have with it, I think the Mustang throttle bodies, some of the Ford throttle bodies, and the C7 Corvette throttle body, I believe, runs a single edge nibble transmission on basically one side. They have an analog voltage for telling you where the basically the throttle blade is at, and they use a single edge nibble transmission on the alternate side, which you may be familiar that for your acceleration pedal, so to speak, you have one side that's going to be a rising sweep, and the other one's going to be a falling sweep when you play with the pedal. So they're always just kind of crossing over each other and going back as you lay into the throttle and lay out. The single edge nibble transmission was a way to get essentially a different reference, and uses just a different technology. So why it came to be, I don't really have a great reason. I don't know where the inherent benefits are compared to an analog signal. It keeps people out of it for the most part. If they wanted to hey, I want to swap a throttle body with a different throttle body, in the performance world, it's not going to be as easy as you thought it would be, most likely. But it has its own packet layout. It does a few things, and it kind of looks like a PWM signal. But it has different pieces that it'll do a high and a low on. So when it drops back low, that means it's basically completed that part of the packet. So you have your initialization or synchronization area, and then it goes into the header, I believe, which tells it just some information, and then it goes into a signal. And there's a few ways that it can be interpreted based on how many signals. I think that you can have up to 2 or 3 signals, depending on what type of CENT protocol you're using.
Okay.
But it looks a lot like a PWM signal. It goes from just basically, I think, a half a volt to somewhere over 4 volts, and it just kind of goes back and forth. And you'll find that if you hook up a kind of like a oscilloscope or some type of waveform tool, you'll see like, hey, like if I'm pressing the throttle, I'm seeing it much higher for a much longer period of time, and then it goes back to doing its little triggering, and it does this. It has its own CRC. It does a lot of stuff with a very, very little bit of space. And outside of that, I've never actually played with it. I've never physically connected to a synth protocol outside of using an aftermarket ECU that you just say, hey, we're running this throttle body. It runs the synth stuff. It does the characterization on the back end, and you don't have to actually, physically reverse engineer it or anything like that. But yeah, it's just an asynchronous protocol that'll typically tell you 1 or 2 signal values to determine information.
Sure. Yeah. That's my experience with them too, is throttle bodies. We had a 14 Cadillac. So that's a pretty old car at this point, for the school when I was teaching there at the college. And what I would do, because I figured out that, the school car has 2 throttle sensors, but only 1 signal wire for the throttle body. And so I'd have the students, I wouldn't exactly explain it to them up front. I want them to kind of search it out. I told them, okay, we're going to be looking at this throttle body. It has 2 sensors. Look at the diagram. It shows you, can you show me both of the signals, right? Because we explained that there's 2 different, but like you say, they're inverse from each other. One will go up, the other one goes down as you move the throttle. And eventually they find out, there's something different happening on this wire. It's a pulse width modulation. It's essentially some form of network communication, right? And that's just to show them that, hey, more and more sensors could be moving this way in the future too, where it's not your analog value. There's a message being sent. Is that throttle body now a module, right? You can make that argument. And I kind of think that's the easiest way to think about it.
Yeah, absolutely. Any peripheral that doesn't, like the way that I look at it is any peripheral device that uses some type of active communication, I consider a module. Mm-hmm. Now, with that being said, you probably don't have any ability to program said module. True. You can't change the metrics inside of it. It's kind of hard coded, just like essentially some blind spot modules, to my knowledge, right? They're programmed from the factory. You put them on the car, and they're done. You don't have to do anything. You go for a dry run on them, and there's no programming involved. They just need to be put in the right spot, and you're good to go. The same instance would occur there, because I don't know if for some type of safety and security standard, I don't really know if I would want to change throttle body aspects to begin with. Right. But 2, they're more of a response device than an action device. They get told what to do, and then they report back what they've been told or what they see. Yeah. That's essentially what a throttle body or a drive-by-wire throttle body is doing. So the motor controller, on the other hand, is essentially the ECU in most circumstances. Mm-hmm. So the engine control unit saying, I'm targeting this. I'm going to send the motor signals via H-bridge to trigger this target position. And it plays with the motor controls to get it to where the target value is. So there's a lot of characterization that goes into a drive-by-wire throttle body, especially at the OE level. I wouldn't say it would be a module that you would need to program or anything like that, and do anything type of active, reprogramming, resetting, stuff like that. So it would be on the side.
Yeah, and I mean, if you look at it with the thought of like a pulse width modulation too, I mean, that goes way back to GM MAF sensors and Ford, like really old Ford MAP sensors would use a frequency. So that idea has been used for a long, long time.
Absolutely.
I think that's fairly straightforward. And what we're looking at is text as it's going to be a square wave. It's going to be a message, but it's one way. And I think that maybe is the one thing to take away from it, is that it's one way communication, not like a LIN bus where it's going back and forth on a single wire.
Yeah, that's correct. Like most of your like bidirectional communications, I can see and can understand how more sensors could be implemented via scent if they have multiple signals embedded in them. I'll use a flex fuel sensor as a good example. All the flex fuel sensors I've seen are a pulse width modulated signal, and the pulse period, as well as the pulse, the duty cycle, controls gives you what the temperature of the fuel is, as well as what the ethanol content is, right? So they're using PWM to basically report two signals via one physical wire.
Okay.
Scent is doing the same thing in a different way via one physical wire. It wouldn't shock me one bit if Mercedes implemented such characteristics into various sensors that they had. The oil they don't have dipsticks on a lot of Mercedes, right?
Right.
They have basically a measuring and metering device in the oil pan that says, "Hey, we have this many quarts in it. We're at this quality and this temperature," and it just reports those back in three pulses. So the first pulse does one of the three, the second pulse does another one of the three, and the third pulse does the last of the three. I went through trying to characterize that, and it was quite obscure, to be honest. I didn't get very far with it, trying to figure out what they're doing too deep, but I also was only just pouring a quart in and giving it another test via the scope.
Gotcha.
I did notice which one changed, but it didn't really line up in some type of linear fashion like I expected it to. So okay. I was like, well, the dash still tells me what I need to, so I don't care, right? It was more just playing with the car and finding out, oh, okay, this is how they do it. So sure. I did play with it. And I actually did inject my own PWM values that I used using Arduino. And the scaling was, if you got the scaling off, it really did argue or cry about it. So you had to really play with the total signal length of all three signals combined. And when you restarted, because if you didn't have that close to what it expected, it was not happy at all.
Okay, just setting errors for like the circuit or what did it do?
Yeah, it would say like oil's like out, like oil 0.
Okay. That's cool. Well, yeah, I think the next two probably maybe take a little bit more to at least wrap my head around. Is the Ethernet and the DoIP, and from my reading, they're kind of connected. They overlap a little bit, so I don't know if we'll bounce back and forth between them, but maybe we can kind of start with Ethernet on cars. And my first question when I started reading, this is a while back when I was doing networks for the school, was, okay, we got our old school single wire stuff that was proprietary to each manufacturer. Then maybe we went to LIN, we added CAN, and then there is Ethernet. It's been in our homes computer networks for a long time. Most of us are familiar with the RJ45 cable or a Cat5 cable. And why isn't it used in cars? Because if you look, it's like 100 times faster at data transfer, right? So
it is. It does have benefits, but there. So we'll go back to what is Ethernet, right? It is basically the wired connections you've come to know and understand. There's actually, even though there's 8 wires that are terminated, typically you're only using 4 of those in the network topology, which is the 4 you'll typically see in automotive Ethernet applications. The only cars that I know that actively run Ethernet are the Rivian, like basically the EV cars, the Rivian and the Tesla. And that's just knowing, I know a developer or an engineer that worked for Rivian, and I was talking to him. I was like, "Hey, I'm going to try to sniff your car." He's like, "Good luck. It's all Ethernet." And I was like, "Oh, okay. Well, I'll give it a try when I get a chance then." But, and for the Teslas, there's a lot of people that do back end, but they all break down. There still can in these cars, right? There's not a lot, that isn't still inherently going to be a controller area network. And there's a couple reasons that I could conclude as to why. And one of them's cost, right? If I look up, I do a lot of random like homebrew development on stuff. And, I'll build stuff with CAN bus microcontrollers and CAN transceivers. And so if I'm looking from a hardware level of what do I need? What is the minimum standard I need to create a CAN bus. I need a CAN bus controller, which may or may not be embedded in a microcontroller, and I need a CAN bus transceiver. Those two things will solve everything I need to create a CAN bus. Now, granted, I don't have a termination resistor in there, but resistors are pretty cheap. And I don't have the voltage controllers or anything like that. That you're going to need that regardless of what application you provide, right? So there's just two devices: the CAN transceiver, and the CAN controller. We'll take the CAN controller out of the mix. It is still inherently cheap, but we'll say it's embedded in the microcontrollers because most of your Ethernet applications are going to have stuff embedded in the microcontroller too. They're not gonna outsource that to another device most of the times, in most cases. So if I look at what's needed from like the transceiver side, and I look at cost, and I'm looking at a retail level. I'm not building 1 million devices a year. I'm not doing great things. I'm just kind of building stuff for my own use cases. I can get a CAN transceiver for like 50 cents to $1. I can get I think it's a switcher, which is what the Ethernet stuff uses, for like $5. So if I'm looking at saying, hey, it's like 10 times more expensive, and what are we gaining? And so most cars are running on a 500K bitrate network. Some of the newer applications have implemented what's called CAN-FD, and we'll get into that a little bit. I'm gonna bring it up in just a little bit on that. But the Ethernet's running most of the stuff is going to be running at like 100 megabits per second on the automotive side. So we got 100 megabits to 1 megabit. So like we're down bandwidth by a factor of 100. But our bandwidth concerns on current applications still haven't been exceeded. So most of the networks that you'll see on a car, they'll just add, I've seen up to 5 CAN buses on a vehicle, right? If you just look at your Alltel scan and look at the topology that you have when you connect to a car, you'll see all the different colors, lines, and they'll tell you what colors they are and what they mean and things like that and what it's connected to. But you're not going to have everything all on the same network in most instances for somewhat of a good reason, right? If one device can take a network down, if we split the network up, we can now isolate our systems. So if we have something that's interior that, we have a noisy node or a fault in a CAN line on some interior functionality, like sure, maybe our AC doesn't work, right? But we can still get down the road. We can still, per se limp it or take it to the shop and say, hey, like this ain't working and none of my interior functions are working. None of the radio isn't doing what it's supposed to do because everything's embedded in the system and it now has AC controls. Those things can coexist, right? So you can have multiple networks doing all the specific functionality and then have essentially a centralized gateway, which will typically be where the data link connector is connected to, in order to communicate anything between any of those devices or any of those networks. So it's the inherent reason that I see why automotive Ethernet isn't applied is cost, and then the cost of time, because uptime on a Ethernet network, like if you turn your PC on, or granted it takes time to boot up, right? But if you said, okay, from the time I like log in, how long does it take to connect to the Ethernet? Well, CAN takes, I don't know, like 1/100th of a second, right? So like if you're driving down the road, keyed off your car, and then keyed your car back on, information it just picks right up because of the way the arbitration process is and the way that the multi-master network exists. With Ethernet, you have basically you're going to have a hub topology that's like, hey, I got to link up and like tell everybody I'm here and tell the router I'm here. And it says, hey, everybody, this guy's here. And you don't have to have that in a CAN network. Okay. So you end up with this layer that's going to take time and it costs you more in order to implement it, and it may not even offer any direct benefits, right? Sure, programming may be a little bit faster if you went directly with Ethernet. If you just had to download a firmware file like you download a file on your PC, great, you're going to be there for 2 seconds versus 7 minutes programming that transmission in that GM, right? That's fine. And I get that. And I'm sure everybody that's programmed a GM transmission can see it takes about 4 seconds to download and it takes about 14 minutes to install. Yep. I understand. I get it. But for the cost of implementation, you drive up the cost and you drive up the complexity, and it doesn't really offer you any meritable benefit.
Yeah, that's not a benefit to the manufacturer necessarily.
No,
So, okay,
no,
that makes sense.
There's reasons where I could say it would be implemented, and I feel that it's coming. In fact, we all know that it's coming. It's just a matter of time. Cars are getting more and more becoming I would like to call it an Internet of Things device. Okay. So your manufacturer, a lot of cars have now they have like Wi-Fi access, or you can basically subscribe to a subscription package, and your car has T-Mobile, AT&T, or Verizon based on where you live. And sure. You can go, oh, okay, like now I have Wi-Fi access, so I can stream Pandora without doing anything directly on my car and stuff. Well, they're going to use that application to go, okay, like any firmware updates we have, like as the aftermarket supplier, it's going to probably hit us a little bit, because any firmware updates that need to occur, they're probably just going to push them to the car while the car's going and say like, hey, the car's off, like we're going to like basically force updates, like Windows force updates on you, and says, hey, yeah, we're restarting your PC, and it's going to take 2 minutes, 3 minutes, 4 minutes, 5 minutes and stuff.
Sure.
So that's where the OE manufacturer could benefit, because they can kind of do continuous development, continuous improvement. But for the grand scheme of things, it also comes with a continual increase in cost and continual complexity, because now you've done, you have, it's all going to be most likely CAN or CAN-FD at the back end for most of these controllers. So you have to have something that becomes essentially a PC in the car to say, hey, yeah, I've got all this, I've downloaded this package or been pushed this package over the internet. Now I got to break it down and push it via CAN to a specific device.
Okay.
So it's always innovative times, right? And things are going to always continually innovate. We're not standing still. The market's not going to stand still for stuff. It's always going to move over to the next new iPhone or whatever, right?
Yep.
So you're gonna see it as time passes that they're gonna do more and more on like internet access and just basically accessing the car remotely at a manufacturer level to push updates.
Yep.
But we're not there yet. I don't think it's going to be for quite some time. I think it's like at least a generation or two out before they really start implementing. You'll see it in like for instance the C8 Corvette, right?
Yeah.
They've done some stuff there, and they'll do it on those applications and go, okay, like. If we have a problem, now we're dealing with just one make and model, not all the makes and models. So it becomes this test bed and this test bench to do such activities.
I gotcha. Is that the Global B platform car? Is that what that is?
So. Yeah.
Okay. Yeah. How about with the ADAS stuff and, in the future with the autonomous vehicle, is that something where that rate of speed might be necessary for data transfer?
I can see where with the cameras, any of your like LiDAR sensors can create a ton of basically data or bandwidth of a high amount of data at a very short period of time. So okay. I can see how information like that could be applied. Cameras inherently, if you've ever seen how much data a camera can create, I mean, just a 1080p camera can create, a few megabits a second, right? Once it's gone through its encoded process and actually applies it to your screen. So those devices that you have the high bandwidth for, sure, absolutely. Like those are going to be where you are going to start seeing a network from. And you're going to see like the autonomous, like the Tesla stuff, it's essentially a PC that's reading, kind of like this real object detection based on the cameras. And each time the frame comes through, is it getting closer? Is it getting farther away? Was it a mirage? Things like that. So they'll utilize that technology in order to keep things moving efficiently. Mm-hmm. But you're still going to see, I still think that you're going to see CAN implemented for like for instance, your engine controller. There's a ton of data that it provides, but it's not going to be a high bandwidth value. Like for each metric you have on a car per se, let's say it takes up to 4 bytes. So if you have, let's say 100 signals from the ECU, let's say 200, and you just say, hey, that's 4 bytes each. Now you're looking at 800 bytes. Let's say a second, right? Mm-hmm. So those values, you have 800 bytes per second, but you have a bus that's capable of 500,000 per second, so to speak.
Okay.
And you break it down and you go, okay, well, like we still have a lot of overload here. And granted, you have the arbitration ID and things like that are going to take up space on the network too. But for the grand scheme, you're getting the data where you need it to, and you're not overloading a network in any manner.
Okay. The reason I asked on that is, so me and Fonzo are working on I want to say it was a 21 Nissan Rogue. And we were doing some programming stuff, but one of the connectors at the ADAS unit that was in the center console wasn't fully like latched in. Like it had a connector assurance clip, kind of like an airbag, and it wasn't fully seated, right? So it set a code for this circuit because this connector, which only had, I think, 3 wires on it, went out to the I don't remember if it was a camera or a radar unit that was in front of the vehicle. And so the code that it set was for Ethernet circuit is what it told us on the scan tool. Now, I don't know, exactly what that meant because it looked like copper wires going into this connector, but we seeded it and it fixed it. But that got me thinking about it, and I was looking at it, that they're using a faster connection to some of these ADAS sensors, which I found is pretty interesting. But also it was interesting to see that they're utilizing, with just the regular twisted, I don't know if it's twisted pair for sure, but just copper wires that we would see used in another network.
Yes. So like it's going to be the same, like for instance, like that Cat5e cable that you have, like there's going to be 2 options that you have on most of those cables. It's going to be solid. Most of them are going to be a solid core wire. That you'd have like cable to cable from your essentially your PC to your router, whatever. Okay. They do make stranded cables, and some stranded cables exist. They're just not as cheap, right?
Sure.
It's just an inherent cost increase because you're putting 10 strands versus 1. But yeah, you'll see that. I do expect cameras to be the Ethernet standard, or essentially pushing data via Ethernet to any of the devices, especially if they're using the cameras for object detection. Okay. If they're not using for object detection, I could see you could literally have them all like your old school TV, the yellow analog RCA input. You could essentially have those all run. A lot of the RV, like these RV backup cameras, and most of the backup cameras you see that are like sold on Amazon, right? They're just the cheap ones.
Sure.
They all are. You could just hook them up to a TV via the yellow RCA cable. If you hook up that signal, it's an analog signal that it outputs.
Yeah.
And I don't know how it works to where it converts it to a video signal, but that it's just literally an analog signal that's transmitted to create a optical image on a TV or screen.
I've scoped them a couple times, and then I have it's a CCTV tester like you use for like a security camera or something like that. And so I can connect the wire and see, do I have a signal there? But I've scoped them, and then I've waved my hand over the camera, or like held it over the camera to see the actual change in the signal. But it's a wild signal. It's very different from what we're used to seeing on a waveform.
Yeah, I don't understand how it works. I haven't dug too deep in it. I have a dash that like a lot of the race dashes will allow a analog signal input for video. Okay. So I actually have a few that I've bought random rear cameras or cameras to hook up to screens, and I'll use those and implement those. And when somebody's like, hey, I need a rear camera for my Motec or AIM or whatever dash that they use that has a video input, I'll be like, all right, here it is. This is your 3-pin signal. You got your 5 volts, you got your 0 volts, your sensor ground, and you've got your analog signal output. Hook this up, you'll be good to go. But yeah, it's wild how it's changed from such a kind of like an analog to a very digital form. But with that being said, it doesn't shock me that that's the way things are going. Everything's gonna continually go more and more to a digital level for most instances on vehicles, because with the analog signal you can have diagnostic lows and highs, right? So let's say your throttle position, right? If it's below, let's say 0.5 volts or above 4.5 volts, it could throw like a diagnostic too low, diagnostic too high. It's outside the window we expect it to be in.
Sure.
With the digital stuff, you can trigger everything that you need. So if it's outside of these bounds, it's outside of another bounds. If it's changing too rapidly, we can communicate all that information instead of being very basic, right? It requires more processing power or more grunt work on processing, but you can do more with essentially less when it comes to the wiring aspects of it.
That makes sense. With the Ethernet, I also read some stuff as far as interference to the system, right? So that a CAN's always been touted as resistance to interference, electromagnetic interference. And that was one reason that auto manufacturers, besides the cost, decided to go with CAN. You got the twisted pair, and it's very resistant to interference to the controller. Is that how familiar with you on that as far as the differences between the two systems there?
So I haven't inherently dealt with Ethernet an automotive application to test anything for how robust it is. I will stress test a lot of stuff on the CAN side. Mm-hmm. From the CAN side, I know most people here watching probably knows, like, hey, you're supposed to have like 60 ohms resistance on the CAN lines. You can, the node length or the stub length, as they call it. So you have your CAN bus, which is supposed to be like one long wire, so to speak, and each wire has like a branch. Those branches, based on an ISO standard, is supposed to only be, I think, basically a foot long. Right.
Oh, okay.
I'm not here to tell you that every manufacturer lives up to that degree.
I got a Ford Fusion that definitely doesn't, but anyways.
Right. And the thing is they set the standard by saying, if you do it this way, we can guarantee that it works.
Okay.
But the reality is I will take things and do things way more aggressively or way off of outside those bounds or those ranges and still get away with it.
Okay.
Like I have devices that I can hook up to each other, no termination resistor whatsoever. I'm running them. Granted, it's only 4 feet, 5 feet, but I'm just testing between one device to another on a bench or on my desk. No problems whatsoever. No termination resistors. None. But it goes to the hardware. It goes into the hardware at the hardware level. So the transceivers have the ability to, they're essentially taking a transistor logic level of low and high from a transmit and receive state on a microcontroller, on a pin, and then converting that out to what you see as the 2.5 volts plus or minus 1 volt. So based on how well that transistor is built and how basically how well it was designed is going to determine what you're able to get away with. So there's transistors transceivers that work great in those environments, and then there's transceivers that don't work that great. And then you have to if you go digging deeper, there's this thing called bit timing. And each microcontroller will have a specific point. So if you've ever looked at a picoscope and saw like CAN waveforms, and you go, oh yeah, there's my dominant there, there's my recessive there, and we're just going to go all the way across, and you just see like basically one state. Well, the microcontrollers will typically break that down, and the goal is to break that down and look at almost at the trailing edge. So while what we see is like, hey, there's the dominant high and dominant low, they actually break it down into like, basically somewhere around 16 slices and go, we're going to pick a point to read it at that slice right there. That is 1/16
of one bit.
Yeah, on one bit. Okay. That's correct. And that's not guaranteed to be the way every microcontroller does it. But that's a way that most transceivers for the bit timing want to calculate it. They want to get in this range somewhere between 75 and 90% so if that bit goes high and it's swinging and it reflects a little bit and it comes back down, it'll read it right here before it takes another drop.
Okay.
So it takes the reflections and doesn't have to worry about them as much, because if you do have a lot of reflections, it lets it kind of run its state, and that's why I believe that's where the termination resistors come into play.
Okay. And that's that kind of answers the question that popped in my head while you were talking. Is I've had vehicles where you lose the terminating resistance and it gets this, like, I don't know, this ringing, like repetitive signal that doesn't look anything like what a CAN network is supposed to look like, and nothing communicates. And then I've had them where, yeah, it's open completely and there's no codes and nobody's upset and everybody's talking fine. So that must be what it comes down to, is how the actual components were built. Yeah,
it's component design. It's basically a trifecta, right? You can take great component design and make a very terrible network and probably eventually cause complications, or you can take a very terrible network and just basically keep things neat and tidy and go, okay, yeah, we've ran it twice as long as what's the recommended value, and we still got away with it. And
Gotcha.
Wolfhard, I think it's Wolfhard Lawrence. There was a book he wrote, and I loosely use it because I haven't seen a lot of people utilize his methodologies outside of putting two 120 ohm terminating resistors at the end of the lines. But you can actually get away with not using termination resistors at the end of the line and use them at every node. But it gets complicated. And it's not that and that's why I think the two termination resistors at the end of the lines is ultimately what you see and what you've come to understand. There's ways where you can make it where it's, hey, I'm running a 1.3, a 1300 ohm resistor at every stub, and every stub is happy, and still get away with it.
Yeah,
based on the book. I haven't actually tested it, but I don't really have a valid need to, because no one's going to take it. You can't implement both. They don't coexist well, so it's not something that I plan on trying to implement.
I gotcha.
It's just it's not gonna be utilized by anybody.
I think it's Volkswagen Audi that I've seen where they put the full terminating resistance, 60 ohms, in the ECM, and then the rest of the network has X amount of resistance. But I didn't know that until I worked on one, and I found that kind of surprising. But that works for them. Their system, it's fine that way. So
I've seen networks that weren't happy with 120, and you throw an extra one in there and bring it down a little bit, and it was happy again.
Okay.
It still meets the criteria. They don't call the CAN network robust for nothing.
Sure. Yeah.
That's the one thing I can say. It's nearly bulletproof unless you do some wild stuff.
Okay. Yeah. How about this DoIP or DoIP or diagnosis over internet protocol? What do you know about that?
Yeah, so I don't have a lot of experience with DoIP, mainly because everything that I have seen implemented with it, it all reverts back to, you guessed it, CAN. So everything goes through essentially like the DoIP standard, right? This is my knowledge on it. You're going to have an IP interface, which is going to be typically like your laptop, right?
Mm-hmm.
And so your laptop's getting basically wrapping this information up, and you have to do some type of security. It may like the YTech stuff, all of the OE scan tools where you have to log in. They may be inclusive to doing DoIP. I'm not certain if it's access to just getting the programs to work locally, or they're actually networking to say, hey, like we're grabbing the information and we're doing things on the back end and not the front end on your laptop.
Gotcha.
But in order to make it work, right, the inline communication to the car is CAN. So you take the CAN stuff and then you go, okay, let's package all this CAN stuff, and I need to know the MAC address or the IP address or your physical network's IP to know that you are who you said you were once we started this conversation, right? So we stack on basically some type of serialized information on top of the CAN message or the communication that we're sending, and saying, hey, this is what we have, this is who I am, and this is where it needs to go, because you now have to tell it where to go on the internet. So you keep wrapping things, and basically it gets really big, so to speak. And granted, this is where this 100 megabits per second kind of comes into play, right? So because you need that type of bandwidth in order to make it an effective solution.
Okay.
And then you get a response with the same thing. It's like, hey, I'm from this. I am sending it to, and then we have information to on the network, and we're going to send basically this address or this message information or this set of messages and information based on what we saw. Okay. So I call it CAN with a lot of games attached to it, because you're going right now, at least for the time being, you're going from a CAN standard and wrapping it up and putting it on basically an IP protocol. And then they're going on the back end and saying, all right, we're going to unpack all this information on, I think, 3 or 4 different layers to get what you said. And then we're going to send back out what we need to say back and get you the information, whether it's a set of information or just a function call, whatever the case may need to be, on your PC to go, okay, now let's send all this back to the car.
Okay. So, but when you get down to the base, actual physical components like the engine control module, you're probably still going to be dealing with a CAN network as far as test issue is concerned. Okay.
Right. So to me, it does bear relevance in some manner. But if you're diagnosing something via DoIP, getting packets to, just the manner of just getting a packet to and from a device is essentially all that matters. Which you're going to see that as time passes, there's a lot of things that have essentially a timeout value per se. So the big struggle that you'll see, I don't know if you're familiar with tester present, right? If you hook up your scan tool to the car, a lot of scan tools will say, "Hey, I'm still here. I'm still here. I'm still here." Okay. Even if you're not doing anything with the car, you just let that Autel sit dormant in your car. It's going to say, "Hey, I'm still here. We still got an active session. I'm still here. We still got an active session." And it'll do things like that in my experience in order to keep things to where, okay, you're still wanting the extended session. You're still wanting the diagnostic session. You're still wanting the programming session. We'll keep continuing this. And if you don't respond back within, let's say, 5 seconds, 10 seconds, we're gonna cut it off. We're done here. You're gonna have to go through the steps all over again, right? Okay. And they do those things in some manner of security, because if you hooked up to the Autel and said, "Hey, let's go, let's start a diagnostic session. I'm gonna start programming," and I go, "Oh, okay, I'm done." And then I get somebody else's nefarious tool and go, "All right, now it took 13 minutes to hook this up on the car. Yeah, let's restart." It goes, "No, we're not here anymore. You lost your time." Okay. And that's where they'll start implementing a little bit of security to it to try to keep people from getting into it. There's also various security measures that have to be implemented on certain applications. I'm sure if you try to use a generic scan tool for enhanced functionality on I think an 18-up Dodge, Jeep, Chrysler, Ram platform, you have to have access to YTech or whatever. You have to pay for it in order to get access to this equipment. Well, they're going to prevent you from doing that using some type of security algorithm. And in most cases that I'll see on the OE side with CAN, it's currently seed key. And what that means, and the best way I can explain it is, let's say my answer, the calculations that I'm giving you is the first one's going to be multiplied by 2, the second one's going to be multiplied by 4, the third one's going to be multiplied by 6, and the fourth one's going to be multiplied by 8. And if I tell you "Hey, my number's 1, you go, "Hey, your number responded is 2. And then I go, "Okay, next question. My number is still 1. And he goes, "All right, now are your numbers 4. Okay, cool. I got you. Now the third question, my number's 1. Okay, your response is 6. And finally, the number's still 1. Okay, your response is the number 8. But it's not that simple, obviously. They have a very complex algorithm that they keep in check. And that's how scan tools have to communicate. And that's why you have to pay for all these subscription services in order to keep things happy, because getting access to that stuff, they say, "Hey, yeah, we've created an algorithm that you're not going to just connect to and send messages to in order to get what you want. You have to get through essentially a paywall at a local level."
Okay. Do you think that is security more for the vehicle itself, so that you can't steal it? Or do you think some of that security so that it's tougher for people to possibly reverse engineer it or something like that? Who are they intending to block from what?
So it's mostly people from keeping people out of the systems that they don't want, right? For instance, like if I'm reverse engineering how they program a transmission, right? They look at me as the bad guy. They look at me as the guy, hey, like we are doing this job as the OE manufacturer. We have to warranty this product. We don't want you messing with it.
Sure.
And quite frankly, I get it, right?
Yep.
But like you're talking about companies that offer like aftermarket reflashing solutions for various reasons or needs, they have to go through the grunt work of figuring out how to get through or past those security algorithms in order to reprogram the car or to reprogram the module that is in the car in order to do whatever it is that they have changed or implemented.
Yep.
And their goal is to prevent people like them from getting access to the information because they don't want it just freely available. Because for one, how many hours did they spend designing and developing the module for the car, right? And even John Deere, like I think John Deere tried to say like, hey, like the modules that you get on your tractors, they don't belong to you. They belong to us. They're our IP. And I don't know where that whole ruling went, but it was really a battle on the right to repair. Right. Yep. So it was things like that. They're trying to keep the device secure because you don't want, here's a good example of odometers and odometer fraud, right? Yeah. You don't want somebody just going, hey, like I figured out how they programmed the dash cluster or the body control module. I found odometer. My car is now at 1,000 miles trying to sell it for 10 times the price.
Sure.
So it's things like that they're trying to keep their devices secure because they don't want just everybody going all willy-nilly and going, hey, yeah, we can change whatever we want, however we want it. Because most of the times when people do that, they don't do it right.
Right.
It's just the nature of the game.
Yeah. Well, and like you were saying too, warranty stuff too. If you're going in there and changing something on a vehicle that's new under warranty, and then the person's going back like, "Hey, I blew out my transmission." Oh, well, you changed all these values and everything. So I get it.
I'm not going to name any names, but I've known a few characters to do some pretty invasive stuff with their cars, and when they eventually blew them up, it's time to put it back to stock and take it back to the dealership. And whatever. It's not I don't have to live with the guilt or that umbrella over my head. It's not my position to go, hey, you shouldn't do that. They just take it and tell me. I shake my head and just look at them and be like, you're the reason why warranty costs go up. But I hope you know it.
Yeah, no kidding.
You're gonna have those people though. It's inevitable, right? But
sure.
I don't know if that's built into the cost of the car, but there's a lot of things that do get built into the cost of a car, and that's probably a factor that they look at, and they probably put that a factor under the umbrella of cars that got destroyed on the dealership lots and stuff. The cars that got destroyed during transit to the dealership. So
yeah.
Who knows?
Yeah, I think I know there already is companies that are adding on the like the secure gateway that you see in the Dodge stuff, like you were saying, 18 and up. Nissan, Hyundai, I believe, started in 22.
18 and Nissan, I believe.
Oh, okay. And I wouldn't be surprised to see more manufacturers go into that way. Going back to what we were talking about, the car being connected to internet, being its own, hotspot with internet connection, right? That adds that area of vulnerability to someone getting in. I'm sure that you've seen the video of the Jeep that was taken over while the guy's driving it, and they turn on the wipers and then they do all this stuff to it, right? And that's why that's part of why the secure gateway came about. But yeah, so now we've got this vector for attack on vehicles, and
right.
It's going to have to get more secure.
Right. And that's the struggle. That's the inherent struggle is you can go, okay, like we have to create a situation to where our communication layer, essentially the gateway or the router, right? It needs to know more information. That's where the security, in my opinion, should lie. Because and they do it via certificates, and I believe the way that they got through access on that is the certificates weren't up to date for the application. And I don't know much about SSL certificates. I'm not here to tell you I'm an expert on them, but that seems to be the route that a lot of vulnerabilities are shown. I don't know if any of the viewers listen or actively view DEF CON videos, but DEF CON goes through a lot of people that have, kind of like some seminars that they have every year. And they'll tell you, hey, like, this is what I did. This is how I did it. And a lot of them actually, they do it not for nefarious gains. But they want to make sure there's a lot of people that play with security and do a lot of security stuff. So they'll actually test the security on their own cars or cars that they have access to and go, hey, like, I found a vulnerability. And so they'll tell the manufacturer and usually they're working for some company and they have some type of, kind of background that shows that they are who they are. So they'll call a manufacturer and say, hey, here's what I got. Here's what I found. Here's what you're doing wrong. Right. And they'll go, most of the times they go, we're open eyes. You're open eyes and ears. Tell us what we need to know, or tell us where where our problems arise. And, and they'll go, okay, yeah, I'm going to give you 60 days to fix it before I go out publicly with it.
Okay.
So now the ball's in their court in order to actually address the problem. And in most cases, it's not, it doesn't have to be like, we need longer time. It's usually fine. But most of the people will tell the manufacturer, like, hey, like, this is what you're doing wrong. And they go, okay, let's work together to fix it, because that's what they're all about. And so, and then once they fix it, though, the vulnerability doesn't exist anymore. So they get to actually publicly disclose what they did and how they did it in order to solve the vulnerability or explain the vulnerability. Okay. And while that usually can look bad on a manufacturer, the fact that they actually took the steps to actually make it more secure and take the steps to getting the security where it needs to be shows that their vested interest is not just to be, oh, okay, well, who are you? Well, who cares? I don't know. I don't care about you. Just scoff you off. That would create a problem for them. They want to keep things happy for both their customers and the security side.
Sure. I bet you that is an interesting job, or I'm sure fun at times to, be the company or the person who is trying to figure out those weak spots in systems and cars and stuff like that. So
the technology sector, I'm sure that most people are aware, has a lot of funding and backing associated with it, because it's just, everything's built on technology. So
yep.
The consulting side, the engineering side, IPsec side has a lot that they'll go, hey, like, for X amount of dollars, we'll come in and explain how there's vulnerabilities in your physical network or inside your business. How is your business secure, right? And the same thing happens for the applications and modules. It's no different on any manner. There's a lot of people that do IPsec physically, so they're like, hey, like, I can figure out how to break into your building without actually being nefarious and like throwing a brick through a window.
Yeah.
How can I get access to your building? And then times they'll come in and say, hey, like, I'll figure out how to gain access to your network without being on your network, and go, okay. And, 30 minutes later, the CFO that hired the guy is clicking a phishing link, and now he's got complete access and he's done, So it's things like that education as well as understanding on all sides has to occur.
Mm-hmm.
The Internet of Things, a lot of the IoT devices, which is where I think the cars are going. They're going to become a Internet of Things. The security side is something to be a little bit concerned about, because if the manufacturers don't get it right, how long will it take before your car is taken over by, if you got some type of autonomous solutions or active cruise control and things like that, and I start sending it messages and it doesn't realize that I wasn't the person, I wasn't the module that it expected to send that message.
Yeah.
How will it know? Right.
Right.
And so it's hard to play into that without understanding all of the realms and all the sides. And unfortunately, I don't understand the IP side well enough to really start digging in to say, hey, yeah, let's see if we can try to hack the security side of this to send it messages wirelessly in order to take it over like it's Hollywood. But it is something that I don't think is alarming, but I do think it is, like, I do have that, I'll always have that doubt in the back of my head is, are they able to take over the car, or are they able to implement anything as an override function in the car?
Sure.
Or if
as simple as like shut the headlights off while you're driving at night. I mean, like that alone could be extremely dangerous and a relatively simple signal to send to a car. Now, how you get through all this stuff, I don't know, but there's that danger for sure.
Yeah. So the thing that I have noticed, and I can tell you that I dealt with this a little bit, is like, for instance, your send protocol. I believe Lin as well as CAN, they have this like CRC embedded, right? So the CRC is done on the back end. You don't know anything about it, but it's when you send that message, the CRC is automatically generated at the microcontroller or the module level, and it's just happy. If you look at it on a scope, that's about the only time you'll ever see it, because most of your CAN bus analyzers or sniffers, they really just look at three different types of values: the arbitration ID, the message length, and the data.
Okay. So
you'll start to see two different methodologies used. One is just is embedding CRC into the data packet, right? And I've had to do this with a BMW. Their steering wheel was a race car. Their steering wheel was a aftermarket steering wheel, a race steering wheel from BMW, and they wanted to utilize a different steering wheel and utilize a keypad that they had put in the car to control the speed limiting and pit limiting functions. So when they hit pits, they have a pit limiter that goes to 35, 40, 45, 50 miles an hour, whatever they set it as, and it's held at that threshold. Well, we started digging, and I started showing them like, hey, like try these signals, because this is your pit limiting function button. This is your pit speeds values. Like just try this and see if it works. And it didn't work. And I go, okay, let me go back to the table. And I started digging a little bit deeper. And I said, all right, I had to dig, but I found that there was a CRC8 value embedded in the data packet. So if that value is not right, which is a value you have to calculate out, and it's kind of a quite cumbersome calculation, and not many like aftermarket devices are natively going to be able to do it. If you don't calculate this right and get it right, it's not accepting that packet as true. It says that packet is incorrect, is wrong, just like the CRC not being right in the data packet in the CRC of the actual message. So they have the CRC that's going to be in every CAN bus message just to make sure that the message is right. They're putting a CRC in the data area as well to make sure that the rest of the message is actually true to what they stated it was.
Interesting.
And that's going to become more and more commonplace, in my opinion. And granted, that was easy to solve for me, but it's because of the tools I have at my disposal. And it was also it's CRC8's got, basically you have 256 different options for it. Not that I'm really wanting to calculate them out manually, but the algorithm process doesn't seem to take too long to try to dig and say, hey, I found this. There's about 4 or 5 different metrics you have. You have the polynomial generator, an initial value that it'll run, potentially a final value that it what's called XOR, exclusive ORs, and then if it's reflective in and reflective out. I'm not going to get too deep into that because it's really developer level, but essentially you have 5 different values that you got to run through. Each message in the data packet has to be ran through this function generator, and out comes another number. And then you keep doing this for each byte in the message until you get to that last byte, and that's what your number is going to be. So if you don't add that number to that message at the data packet in the specific location, it says the rest of that message, regardless, is junk. Throw it out. So there is a little bit of security associated with it, but it doesn't mean that like if I can break it, I'm just like I'm not that smart. Like I'm dedicated, but I'm not a genius. I'm not a savant with technology. I can't even get my printer to work. Okay, so let's not get it twisted here. It's just a matter of me having a lot of experience with something. But yeah, it's just things that you're gonna, they're gonna have to stack layers. And what you do is you add security. There's other things that they've added for security level access at the physical level at the data link connector for certain applications. And to my knowledge, the C8 Corvette is running cryptography. Now, how to explain that is that I don't know how to. There's no calculation on it to my knowledge that I understand. It's just like the AES 256 cryptography is done. I don't understand it. There's a cryptographic standard for the C8 Vet on the CAN communication as well. So everything on that bus, to my knowledge, is cryptographic. So you're not finding answers all too easily on that network. And I've been told that there's a bounty to solving it.
Interesting.
So yeah, we'll see as time passes if somebody can actually figure out what they're doing. But as of right now, to my knowledge, nobody has. Just actually understanding the CAN network's information. It's just all gobbledygook. There's you press the steering, turn the steering wheel left and right. There's no numbers increasing and decreasing. It's the whole message changing.
Interesting. That's wild. That's and I feel like we were saying, more and more manufacturers go into a higher level of security for stuff, but there are really smart people out there that seem to figure this stuff out eventually, one way or another.
Right.
That's cool. That's really interesting. But yeah, I think we covered those questions pretty well and then some. So I really appreciate your time this afternoon with me. That was awesome.
It's not a problem. For the DoIP, like I have high expectations of essentially it just getting more and more complex because it never gets simpler. Let's just be honest with ourselves, right? It's always going to get more and more complex. But the thing is it, like anything that we do as a technician, it's breaking it down to understanding the steps. Okay. So if we can continually keep breaking things down to understanding the steps and understanding the sequences, we're still going to be okay. Like, I don't think that it's going to be something where we go, hey, yeah, our hands are out. We don't know what to do. We'll never know what to do. The manufacturers are the only thing that knows what to do. The only thing we can recommend is just replacing the module and taking it to the dealer. I don't think that we're going to get to that point.
Right.
I have expectations that it'll never get to that point because there's always going to be a demand for the aftermarket technician and the third-party techs to solving problems because the dealers I've seen, sometimes they get it wrong. It's not, we're all people here. And it's all scopes of interest. And if you throw enough, I've heard on other podcasts, like if you're right 80% of the time, your boss is going to be happy, so it leaves 20% on the table for us to improve upon. So if one out of every five cars needs to be accurately solved because it wasn't solved right the first time, I still think that we'll still hold position.
Yeah. I think a increase in complexity of stuff is a good thing for someone who is willing to learn and better themselves and figure this stuff out because it makes less people, it just inherently creates less people who can figure that out. Right. And so that's better for the people who are willing to strive and try to figure out and solve those problems because you're going to be sought after. You're going to be able to, seek higher wages. That's a good thing for you. So early in my career, I would think the opposite about complex stuff. Like, I don't want this to get more difficult. I already know how to do this. I don't want to figure out something new, but that's where the success lies is seeking that out.
Yeah. I don't think I got involved in the racing world because I didn't understand things or didn't drive myself to understanding like CAN at a very esoteric level. And quite frankly, it's served me well. I get calls, texts, questions nearly daily on, hey, I'm trying to figure out X, Y, Z. Do you know anything about it? Whatever the case may need to be. And it's like, yeah, I didn't like, I'm not hitting these people up like, oh yeah, you should know who I am. I'm Mr. Hot guy that, hot shot here in CAN. It's just like, hey, yeah, I've seen your work. I've seen what you do. Like 10 years ago, I couldn't tell you what CAN was. 5 years ago, I thought I was pretty good. And today I'll tell you, I still wasn't that great. So it's in 5 or 10 years from now, I'll tell you that I was terrible now. That's how it's going to go.
Sure. That's a good thing, though. You want to be able to look back and say, I improved from where I was 5 years ago. If you say I'm at the same or lower, that's a problem, right?
Right. Yeah. I stalemated here. No, yeah. So,
yeah.
But yeah.
Cool, man. Well, hey, thank you again for spending the time with me today. I really appreciate it.
It's not a problem. I look forward to seeing what future challenges we have.
I like it.
You have a good one.
All right, that's going to do it for today's episode. Big thank you to Mitch for joining me on the show. That was really cool. I learned a bunch. Happy to have him on anytime. Hopefully you enjoyed it as well. Want to give a big shout out to everyone listening. Thank you as well. Definitely appreciate that. But with all of that out of the way, let's all get out there and start fixing the world one car at a time.